Good morning, class. We've now finished chapter 6 and move on to chapter 7. Section 7.1 deals with sampling distributions and the central limit theorem. We have established the fact that sampling is an essential part of the statistical process. Let's think about this and ask ourselves why. First of all, it allows researchers to obtain data from a subset of the population, making the data more manageable. It also saves time and money. Even when the population being studied is as large as the US, about 330 million people, researchers often need to sample just a few thousand people in order to understand everyone. Once an appropriate sample, if we want to dig a little deeper into sampling techniques, we can read section 1.3 on our own, has been gathered. What do we do next? How does a statistician evaluate the significance of sample results? We begin to answer this question by first looking at sampling distributions. This is a distribution of the values of a particular sample statistic for all possible samples of a given size n. We first look at some commonly used statistics and their corresponding parameters. So remember that the mean for a sample was represented by x bar, however, for a population was represented by mu. The standard deviation was represented by s, and for the population, represented by sigma. And the variance, remember, is the square of these values. Now, we have not discussed this statement yet, proportion. We've talked about it maybe a little bit. You might remember from our section 5.2, the binomial. This p looks like our binomial probability of success. And in fact, it is. But we haven't talked about this sample proportion, p hat. And we'll talk about that later in this chapter. Let's consider an example. Pinedale, Wisconsin is a rural community with a children's fishing pond. Posted rules state that all fish under 6 inches must be returned to the pond. Only children under 12 years old may fish, and a limit of 5 fish may be kept per day. Susan is a college student who was hired by the community last summer to make sure the rules were obeyed and to see that the children were safe from accidents. As a project for her biometrics class, Susan selected 100 children at random and listed the lengths to the nearest inch of each of the 5 trout caught by a child in the sample last summer. For each child, she listed the mean length of the 5 trout that the child caught. Now, let us turn our attention to the following question. What is the average length of a trout taken from the Pinedale Children's Pond last summer? To answer this question, we can do the following. First, we list out all of our data, being sure that we keep track of the 5 lengths for each child in the sample, along with their respective mean. So here are our 100 samplings. So here's the first 50, here's the second 50, and for each number, this represents a child. So number 15, this child caught 5 fish, one of length 9 inches, one of length 11 inches, one of length 9 inches, one of length 10 inches, and the last of length 10 inches. And what Susan has done is taken the average x bar of these 5 data values and gotten an average trout length of 9.8. Next, we can use techniques from chapter 2 to create a frequency distribution for the mean that also portrays the relative frequency. So what we do is we look at all of our sample means. So we have 10.8, 9.8, 10.4, 10.6, 11.2, so forth. And we create a frequency distribution, so any x bar that's between 8.39 and 8.76, we see that there's 1. Any x bar that's between 8.77 and 9.14, we see that there's 5 of those, and so forth. And then we look at the relative frequency. Now remember from chapter 4, relative frequency is just a probability. It's an experimental probability. If we plot this distribution using a histogram, or also known as a bar graph, we see that the shape of the distribution looks like a normal curve. It turns out we can approximate the frequency distribution using a normal curve. And we in fact saw that in section 6.5 of chapter 6. The bar graph is symmetric, so we can approximate it using a bell-shaped curve. The bell-shaped curve represents the theoretical probability distribution that would be obtained if the number of children were much larger. This is our first example of a probability sampling distribution for the sample mean, x bar, of trout lengths based on random samples of size 5, because each kid was allowed to catch 5 trout. A sampling distribution is a distribution of the values of a particular sample statistic for all possible samples of a given size n. For this class, we will consider 2 sampling distributions. The sampling distribution of sample means, we will call this the x bar distribution, since a sample mean is represented by x bar, and the sampling distribution of sample proportions, and we'll call this the p hat distribution. This notation here, it looks like P is wearing a little hat. This is our sample proportion. Again, we'll talk about later in this chapter, and we'll call this the p hat distribution. So a fact, the following hold for any sampling distribution of sample means. The mean of a sampling distribution of sample means, denoted by mu of x bar, equals the mean of the population, mu. Now notice these are equal, but we're distinguishing the difference. Mu is coming from our regular x distribution that we've talked about all throughout chapter 6. However, this mu is coming from this new distribution. So we want to let the reader know by labeling it mu sub x bar. This is coming from the x bar distribution. And remember that this is just saying the highest point of our bell shape on this normal distribution is exactly where the highest point of this bell curve is for this distribution. So the peaks are at the exact same value. That's all that's saying. The standard deviation of a sampling distribution of sample means, denoted by sigma of x bar, again, we want to distinguish which bell curve it's coming from, equals the standard deviation of the population, sigma, divided by the square root of the sample size. So notice that whatever sigma is, since we're dividing by a positive number, this standard deviation is going to be smaller, meaning this distribution is going to be more peaked. It's going to be more narrow and taller than the original x distribution. So if this is our population distribution, this is our sampling distribution with n equals 5. Notice it's more peaked. They're centered at the same value, but this one is more peaked because the standard deviation is smaller. And if we changed our sample size, we don't have to use 5. If we changed our sample size to 30, our sampling distribution would be even more peaked because we're dividing by a larger number. And we can superimpose these and see they're all centered at mu. However, the larger n gives us a more peaked normal curve, bell-shaped curve. Let's look at an example. suppose that movie ticket prices in one area have a mean of $8.32 and a standard deviation of 72 cents. Ticket prices are recorded for samples of 52 theaters. Calculate the mean of the resulting sampling distribution. We know the mean of a sampling distribution is equal to the mean of the regular distribution, the population distribution. So we see that the mean is $8.32. Now, if we want to calculate the standard deviation of the resulting sampling distribution, we use our formula. Remember that it's given by the original standard deviation divided by the square root of the sample size. So we have 0.72 divided by the square root of 52, since we're sampling 52 theaters, and we get approximately 0.099846. The central limit theorem states that as the sample size n of a sampling distribution increases, the sampling distribution begins to approximate a normal distribution, regardless of the population distribution. Furthermore, the larger the value of n, the better the normal approximation will be. We have the following fact: a normal distribution may be used to approximate a sampling distribution of sample means if either the sample size is at least 30, so n is greater than or equal to 30, or the problem states that the population is normally distributed or approximately normally distributed.